exponential functions. So here we have a situation where, and this reminds me of a question that someone asked me when I was younger. Would you rather have a penny on the first day, then double it for the second day, double it on the third day, right? So 1 penny, 2 pennies, 4 pennies, 8 pennies, 16, 32, and so on and so forth for a month? Or would you rather have $100 a day for a month? And me being the naive student, I took the $100 a month, $100 a day for a month to get my $3,000. Little did I know that when you charted it out and put it in a table and you saw that, on the 10th day, you end up with $5.12. On the 20th day, you end up with $5,242.88. You have far exceeded what you would get in 30 days of $100 versus. So as you can see, when you use this function, you could just jump to whatever day in the month that you're actually trying to calculate how much money you get. So that's kind of a cool introduction to exponential functions. Okay, so there are specific qualities of exponential functions that they all share. So let's take these three different functions: 2 to the x power, 5 to the x power, and pi to the x power. And as you can see, they're all graphed, and there's properties. So first of all, the domain of all these, as you can see, the line goes indefinitely to the left, infinitely to the left, so it's negative infinity to positive infinity. So the domain will be all real numbers. Now the range is different. The range increases forever, but look, it never actually crosses the x-axis. So the range is basically y is greater than 0. Okay? Number 5, this is an important one. Each function has an asymptote at y equals 0. Now an asymptote is a word that basically means a line, horizontal or vertical, or diagonal really, that a graph approaches but never actually reaches. So as you can see, all three of these graphs approach y equals 0. They approach the x-axis, but they never actually touch the x-axis. And that is a horizontal asymptote. None of the functions have a vertical asymptote, and the functions all intersect at 0, 1. And the reason why these all intersect at 0, 1 is because 5 to the 0 power equals 1. 2 to the 0 power equals 1, and pi to the 0 power equals 1. Anytime the x value is 0, the y value is 1, and that's why all of them intersect at the point 0, 1. Here's the important takeaway from today's lesson. When the base of the exponent is greater than 1, it is a growth factor. It is exponential growth. When the base of the exponent is less than 1, but greater than 0, it is decay, exponential decay. So some examples of exponential growth: you have world population, money in the bank. Exponential decay would be half-life of a drug, depreciation of a car. So very quickly, look at this function, and this function. As you can see, the change factor 1.2, this is the base. It is greater than 1, so it's growth. 1/3 is less than 1, so it's decay, and 0.25 is less than 1, so it's also decay. The height of a bouncing ball after x bounces is represented by this function, 80 times 0.5 to the x power. So right away I notice that's 0.5, so it's decay. And if you think about it, it makes sense because you drop a ball and gravity takes over and it starts to be lower and lower. So after one bounce, they want to know how many times higher the first bounce is than the fourth bounce. After one bounce, the height is 40. After 4 bounces, the height is 5. Well, that makes sense because half of 80 is 40, half of 40 is 20, 10, then down to 5. So how many times higher is the first bounce than the fourth bounce? Well, 40 divided by 5 is 8. So it's 8 times higher. A population of wolves in a county is represented by the equation P of t equals 80 times 0.98 to the t power, where t is the number of years since 1998. Predict the number of wolves in the population in the year 2008. So t equals 10 because from 2008 to 1998 there have been 10 years. So we simply take 10 and we put it in as the input. P of 10 equals 80 times 0.98 to the 10th power. Carefully plugging into our calculator, we end up with 65.365. Now we don't need the decimals because there's no such thing as 0.365 of a wolf. So 65 wolves is the population in the year 2008, and as you can see, they have been dying off. We started with 80 down to 65. What was the population in 1998? Well, in 1998 is when t was 0, t equals 0 in 1998. So when you put 0 into the function, any number raised to the power of 0 is 1, and 80 times 1 is 80. And that makes sense because we start off with 80 wolves. Finally, we have a financial example. Here we have the Franklins inherited $3,500, which they want to invest for their child's future. I'm going to highlight the pertinent information as we read through. If they invest at a 8.25% with interest compounded monthly, determine the value of the account in dollars after 5 years. Using this formula, where A equals the value of the investment after T years, P is the principal invested, and R is the annual interest rate. N is the number of times compounded per year. So we got a lot of input values. We have P equals 3,500, R equals 0.0825 because you always must change a percent to a decimal. N equals 12, and T equals 5. So we carefully plug all these pieces into our formula. And what I do is when I calculate this, I calculate a chunk at a time. I first calculate the parentheses, 1 plus 0.0825 divided by 12. I also raise it to a power of 60. I went ahead and did 5 times 12 in my head to get 60. And I end up with 1.5 and some change here. Multiply it by 3,500, and my answer is $5,279.61. Okay, that is today's lesson. Best of luck to you.